Is the screen visible now?
Yes, it is.
Okay, so now I'll start my presentation. So as you would have already seen, the topic of today, the main topic of today is the Jordan form of a linear operator. So all the lectures you have seen so far have covered many things, including the basics of vector spaces and eigenvalues and eigenvectors. You've also seen the spectral theorem for normal operators on inner product spaces. So continuing this, we'll see today this Jordan form of a linear operator. So one thing I want to say is that yesterday's lecture and many of the things done in yesterday's lecture by Dr. Tiju Cherian are very important for today's talk. So if you have not already seen it, you should go back and watch it so that there is more continuity when you come to this part of the workshop. Okay, so the goal of the lecture is what I'll talk about now. You already saw that the spectral theorem for a normal operator T on a complex in a product space V gives a decomposition of V as some direct sum of eigenspaces. These are all definitions you have seen. And you saw that you get a very nice diagonal form for T. So why did we want diagonalizability? You have already heard it makes many things very easy when the matrix of an operator has some simple form. So if it's diagonal, that's great. That's the best possible case. But in some cases, that's not possible. And then the next thing you hope for is an upper triangular form. So some of these things were mentioned in the previous lectures, especially yesterday's lecture. So what we will show today is that any linear operator T on a complex vector space, so it does not have to be an inner product space or a normal operator, will show that any linear operator has a block diagonal matrix. So I will define what this means. But roughly speaking, it is a matrix where there are blocks on the diagonals, and each of these blocks is upper triangular. So there exists some basis of B which comes from generalized eigenvectors such that the matrix of T has this particular form. And what makes this form very nice? You have already seen upper triangularization of a matrix. When you have this kind of block diagonal matrix consisting of upper triangular blocks, what it actually means is that the matrix has even more zeros because of the block form. And you'll see how that looks. The next thing is we look at refining this result to get what is known as the Jordan form of a linear operator, which will show that each of these upper triangular blocks has an even simpler form. So to be precise, in this upper triangular form of each block, the diagonal elements will be the corresponding eigenvalues for that generalized eigenvector space, and the line above this diagonal will have ones and everything else is zero. So that's a very simple form, and this means you can do, if you're looking at matrix multiplication, for example, that becomes so much simpler because, as we all know, matrix multiplication is not an easy thing in general, right? Even for us, and even when you are doing it via a code. So when you make the matrix as simple as possible with respect to some basis, then it is very nice for such things. So that was just to summarize what we will be covering today. So if you're looking for some keywords and definitions that we will be looking at, here are a few. You have already seen what generalized eigenvectors and generalized eigenspaces are yesterday. I will just go over these definitions quickly again. We'll look at nilpotent operators. We'll define what algebraic multiplicity means. As I mentioned just now, we'll define what a block diagonal matrix is and what a Jordan basis is. So this is the main goal of this lecture. And all this material comes from chapter 8 of Sheldon Axler's book. Now, if time permits, I will go into these things which are in section C, so chapter 8C of Axler's book, where he discusses characteristic polynomial, minimal polynomial, the Cayley-Hamilton theorem, and a few other things. So I think we will have enough time to do this, but let us see. So the main goal will be to arrive at this Jordan decomposition, and if we have time, we'll move on to these other things. So like I just said, this material is taken from chapter 8 of Sheldon Axler's Linear Algebra Done Right. As others might have mentioned already, it's a very nice book that explains things in a very clear way. So I really feel, as others have said, that Vinay can pick up this book and understand things, and all of us have taken our material from this book. So many thanks to the author for having explained things so clearly. If you see any mistakes or typos in these slides, they are my own, so not anybody else's. And thanks to all of you for attending this workshop, even though it is a holiday today. And also, as I said in the beginning, thanks to the organizers for giving me this chance to be a part of this workshop. So the first few slides, I'll spend quite a bit of time just recapping what is already done. One thing I want to say is what Dr. Gayatri Verma said in lecture 2, that even if you do not understand every single thing that happens in the lecture, understand in the sense of knowing every line of the proof, it doesn't matter. The main goal is to take away the main results and to know that if you go back and look at the proof in the book or the notes, you will be able to understand it. So this material for the first time, we definitely did not understand it the very first go. So it's always nice to recap these things. So I'm just going to recall a few results from lecture 4. So the first thing was to drive in why it is so nice to have an upper triangular form for a matrix. So in the rest of the talk, we'll always be looking at, I've written here a complex vector space, but I should say that sometimes for some results, we need that the vector space is a complex vector space. It is okay if the vector space is real or complex. So so here's the first typo. But after this, I think everything else will be specified for that particular result. So in general, if we have a vector space, we have dimension n. L denotes a set of linear operators on B. This will be consistent throughout the slides. So having established that, let us recall some results from lecture 4, yesterday's lecture. Suppose T is a linear operator on some vector space V, and suppose its matrix with respect to some basis is upper triangular. That means it has this form, right? So everything below the diagonal is 0, and you have these elements on the diagonal and some star here. So these could be any entries. Then you saw that T is invertible if and only if lambda j is not equal to 0 for every j. And using this result, you also saw that if you take some linear operator on a vector space T, on a vector space V, and suppose its matrix with respect to some basis is upper triangular, then the eigenvalues of T are precisely the diagonal entries of the matrix T. So this is to again emphasize why an upper triangular matrix is so nice. You already saw this property for diagonal matrices, but it is true even for upper triangular matrices. Okay, so some more recap. This null of S will denote the null space of S for any operator S in L of V. So to recall what is the null space, it is all those vectors in V which get sent to 0 under the linear map S. So one thing to remember is that the 0 vector will always belong to the null space of S for any operator S. And then you saw this theorem which says that the null spaces of powers of an operator, these are increasing as given here. So here is my first typo. Let me correct it right here. Sorry about that. So this should be to the power 0. So this is actually identity. So the null space of T to the power 0, which is identity, is just the result inside 0. And this result inside 0. And this is contained in the null space of T, which is contained in the null space of T square, and so on and so forth. In general, for any k, the null space of t to the power k minus 1 is contained in the null space of t to the power k. This goes on. So this should be t to the power 0, which is the identity operator. Apologies for that error, but I've changed it now. Then you also saw that if you take t, a linear operator on a vector space V, and m is some non-negative integer such that the null space of t to the power m is equal to the null space of t to the power of m plus 1. So if at some stage in this increasing chain, two of these null spaces become is equal to the null space of and so on and so forth. Let me just make that correction here also. This is null space of t to the power 0. That is what is equal to 0. Okay. And then another theorem that you saw is that null spaces stop growing. Because we are in a finite dimensional vector space, after a certain stage, the null spaces cannot keep growing. So, because the null space of any operator is sitting inside V. So, suppose the dimension of V is n, and t is a linear operator on V, then the null space of t to the power n is equal to the null space of t to the power n plus 1. And further, you can always decompose V into this direct sum. Is the dimension of V. This is not true for every. Once you take t to the power of the dimension of V, which is n, then you get this direct sum decomposition. Okay, so so far we looked at some properties of the null space, just to recall. And before that, we looked at what happens if you have an upper triangular matrix. When is it invertible? What are its eigenvalues and so on. So I'm just recapping so far. So now we'll recap. You would have seen this many times now, but I will just go over them again. Eigenvectors. So let T be the space B, and lambda is some scalar coming from an eigenvector of T corresponding to the eigenvalue lambda. Let me again say that this should be F. Okay, so it can be C or R, but this is just to be consistent. So you know what an eigenvector is. You get what is known as the eigenspace